In this video, we're going to explore a slightly more challenging integral that lends itself to integration by parts, and that's the integral of x squared cos of x. It's worth always thinking in terms of process. Would a substitution work in this integral? Because substitutions are usually easier and more straightforward than integration by parts if they work. It's worth looking at this and saying, would a substitution help? And it turns out here, if you go through some early diagnostics, that it won't, because the inside function here, that's the problem, is the x inside the cosine. Its derivative isn't outside. We have this x squared as a multiplier, not inside another function. So it doesn't look like substitution is a natural fit here. If that's the case, then integration by parts is our next fallback. And for that integration by parts process, we need to choose a u and a dv part. Take a look at the options that are listed here and see if you can identify one that looks like it has better prospects for success out of the set here. Pause the video and then we'll check in. Okay, let's remember our guidelines. Whatever we define to be u, we want the u prime to be simpler, and for the dv, we have to be able to integrate it. Able to integrate. And as a secondary thing, if we can't integrate it, then we want the integral to be simpler. Be more explicit here, the integral of dv should be simpler. Well, we quickly run into some problems with these first two options because here, if this is our dv, we don't know what the integral of x cos x is. That's why we're having this problem in the first place. So that's off the table. The integral of x cos x here, we've actually worked with that as an earlier process. So let's save that for later. Cos of x here, this looks promising because I definitely can integrate cos of x. And when we take a look at the derivative here, we'll get 2x. We have x squared. We're going down to x's to the power 1. That has a feel of something that is going to simplify our process. Looking at this last option, if we take a look at the u part, the du dx requires the product rule. And again, there's nothing wrong with that, but it's going to mean very complicated du dx form when we're done, so it's not what I would try first. So this one here, option C, is what we're going to try as a first step. U equals x squared, and the dv being the cos of x dx part. So let's put that into motion. Again, we choose our u and our dv's. And once we've done that, we turn a crank. There's a process that leads to the integration by parts result, which gives us a new integral. And all we ask is, have we made progress by creating a new, simpler integral, or has it gotten worse somehow? We should try something else. But once you've made this choice, there are no more choices for the next little bit. Our du dx would be the derivative of u, and so that would be 2x, and we usually write that explicitly as the du. That should be 2x dx. There we go. Next, we do the integral of the dv part, and that gives us v. What do we differentiate to get cos? We differentiate sine. And that's all the steps complete here. We now need just to fill in the integration by parts formula. It's often convenient here to label the first integral some letter so we can tidy up or at least simplify how much we're copying. This original integral, because we've divided into u and dv parts and applied these calculations, we can now replace with the udv formula, sorry, uv out front, integration by parts, uv x squared sine of x minus the integral of v du. And that is v sine of x, and du is 2x dx. Notice there's always, with the integrals, d's, and once we get to regular expressions with no integrals, there's no d anything in these expressions. All right, Then tidying up, just so we can take a closer look at what we actually have. We have x squared sine of x, and that's essentially dealt with. Minus 2, and we would typically write this as x sine of x dx. This part's complete. Now we evaluate our integral just to see whether we got something simpler, and I would argue that we have. We started with x squared times a trig. Now we just have an x times a trig. But can we evaluate right now or by a simple antiderivative? And there, I think, is where we hit a problem, because this is not a simple function to anti-differentiate because of the product, x times sine of x. So where does that leave us? Well, it leaves us faced with a new integral. Let's call this here I2. But it is a perfect candidate for integration by parts again. We have x times sine of x. If we pick our u and dv, I think we can get this down to a new integral that's just sine, following the idea that we had x squared cos. We got rid of 1x to have x sine. If we do that process again, we should be able to get rid of that x. And that's our inspiration. Let's do that here. I'm going to call these u and v again, the sort of local copies of this idea. We're going to pick x for u and our sine x dx for dv. When we do that, the derivative is 1, and what we typically do is write out the derivative. That's where this calculation is getting the 1 from on the right-hand side. But we often put the dx immediately on the right-hand side, knowing the process that we're using. Similarly, for the v's, we get the integral of sine. What do we differentiate to get sine? We differentiate negative cos of x. And away we go. So this new integral can be evaluated through this process here. Let's write some of that out on the next page. So we did one application of integration by parts to get this formula. And then we did a second application of integration by parts, and it's going to fill in a replacement for this integral. Going back one page, we have u and v, which will be x times negative cos of x. Notice the negative 2 is multiplying this entire integral, so that negative 2 will multiply this entire expression here. Minus the integral of, going back a page, v du, negative cos x dx. So it's very common to have multiple negative signs running around in these expressions. Just be careful how you handle them. But this is a wonderful step forward. Let's do one tidying round just to make sure we can all see that we've made some progress. X squared sine of x minus 2 times negative x cos of x. The double negative here turns into a positive. And then our last new integral, the thing we traded our original x squared cos of x integral for, is just the integral of cos of x. And this is definitely simpler, and we can actually do it by inspection. So now we're going to do the final integration step, where we actually take an antiderivative, x squared sine of x minus 2 times negative x cos of x plus, what do we differentiate to get cos? We differentiate sine. And I usually put the plus c adjacent to the integral here. It gets multiplied by negative 2. Some people prefer to put the plus c at the end. It doesn't actually have any effect on the final form or the meaning of the final answer. That's it. We are done. If we differentiated this function here, it would be complicated for a couple of steps, but it would then simplify down to x squared cos of x. Not at all obvious on the face of it, but in this case here, by applying integration by parts once, and then integration by parts again, we simplified our original integral to one that we could evaluate along with some extra corrective terms, and we've constructed a full antiderivative for that complicated function.